we'll look at a few different approaches for collision handling. First, let's make sure that we're clear on the idea of what a collision looks like. In our previous hash table example, we had 4 keys and they all mapped to unique locations in the hash table. Then, if we add a new key, there's always a chance that it might map to a location that's already filled, like how Karen maps in this case to the same location as Andre does. For whatever reason, whatever the math is, whatever mod we're doing here, sometimes things will map to the same index. And this will cause a problem for us because we need to know how to store that new value since its space is already occupied. And there are a few different approaches we can take to that. So a collision occurs when a key hashes to an index that's already occupied by another key. It tends to occur more often when either the hash function is not very uniform, so it returns the same values too often, or the load factor has gotten too close to 1, or even greater than 0.5 is sometimes too risky for us, because the load factor, again, remember, is the percentage of the table that's already filled. So obviously, as the table gets more and more filled, if we still have data to add, if we still have keys to add to the hash table, the likelihood that we'll have a collision, keys mapping to the same index, is higher the more full our table is. So we can look a little bit at how the probability of the collision could grow. Here's a metaphor for it. If we said for people that we just used their birthday as the hash, then having the same birthday would mean hashing to the same index, let's say. So among people, it only takes about 23 people in a group for us to have a greater than 50% chance that 2 of them will have the same birthday. And the more people you add to your data structure, the more likely it is you'll have collisions like this. So the more data you have to add, the more likely the collisions, and the less well distributed the hash function is, the more likely you'll have collisions. And there's a certain level at which you're obviously always going to have collisions. If you have 368 people in a room, you're going to have some collisions among their birthdays. So here we've got a function where if we assume no leap days, then 365 is the number that's used to kind of show us the likelihood that we'll have a collision in this hash table that uses birthdays. So we have to have some collision resolution strategy if we know that we're not in the perfect situation where our array perfectly fits all possible keys and our hash function perfectly gives us unique values for all possible keys. That's pretty rare, so we'll look at some approaches to handle when those collisions occur. There's separate chaining, which is sometimes referred to as open hashing. This is where you just create a bucket for each index that allows more things to be stored there. It can be a fixed bucket like an array, or it can be something like a linked list, and each one will have its ups and downs, just like we often have in data structures. We can also do open addressing, sometimes called closed hashing. Open hashing is called open hashing because it sort of opens more space. Closed hashing is called closed hashing because we still just use the indexes in the hash table. We don't create any more space. We just kind of fudge where things are allowed to go when there's enough space to fill in. There are some other approaches that we'll look at. Rehashing can be done with using another hash to try to sort of help distribute things, but this is usually done when things get really bad. And then there's cuckoo hashing. We won't look at those right now, however. So separate chaining is pretty simple. Instead of having, say, an integer or a string or whatever your key is stored at each location, you create a data structure of that key type, like a linked list of strings or a linked list of integers. This allows us to attach some bucket that can catch more than one thing to each index, so that when keys collide, we just add them onto that list, or we just put them into that array that's there, or whatever. It's often fine to use a simple linked list. The reasons why in this case are a linked list can grow infinitely, so we don't have to worry about running out of space again. An array would possibly give us faster lookups. We might be able to sort it and do binary search within it, but then our bucket's going to run out of space and we're back in the same problem we had before. So unless we know the right value for bucket sizes, then a linked list will usually get by just fine. It will take a hit on performance, but there's zero extra cost for the empty cells. We don't have some array sitting there empty, and we don't have to use a large amount of extra storage for it, and it can grow. And it's a pretty low cost to traverse these small lists. So if our distribution is good, if our collisions are low, it's not too bad to step through a small list of items. That's certainly much better than stepping through a list of all of the original data without the hashing. And we really only need the equals operator. We're not doing comparisons with them like we might have to do if we were trying to do a binary search on an array inside of there and keep that array sorted. There are other possibilities, like using a tree under there. So we have maybe a binary search tree under there that gives us faster lookup. We could use a second hash table inside of there, though then we would need another hash function. And as I mentioned, we could use an array, but it will have all the drawbacks we see with arrays, limited size, and having to keep it sorted when we insert or remove. So if the load factor of lambda is larger than 1, we're still going to be just fine for separate chaining here. We're not going to run out of space when every slot in the hash table fills. The other common approach is going to be limited in terms of the space in that regard. It's called open addressing. So here we only strictly allow one key at each table entry in the hash table. We're not going to add on lists and sort of grow outward. We're going to, when two objects hash to the same index, just look for another spot in the hash table for them to go to. And you can probably already start to imagine some of the complications with this, but it doesn't add extra memory use, and it has some other beneficial features to it. So the first one that hashes to a particular location gets that spot. And then next ones that hash to that location have to find somewhere else to be in the table. Sorry, the seat's taken, you've got to sit at the next one back kind of situation there. So we have to have a load factor that is less than or equal to 1 because we cannot fill more than the slots that are available in our hash table. We're not growing here. And the performance will degrade as the number of collisions increase, which is also true for the other options, but here we'll degrade faster because we have to do some more work to find where a thing went. And then the problem is thinking of a strategy to find that new index. When something else maps to index 1, what can we do to find a new index for it? And what problems will we encounter? For example, in this one shown here, now when something maps to index 2 is filled with something that should have been a 1. And so we're going to encounter some difficulties with it. What we'll need is probing to solve this problem. Probing is just the word for how we find that next location that something should go to. We have some collision resolution function, and we say that f of 0 gives us 0, and we store the key at the first empty index. So we try some number, and we see if it's possible, and we will do mod of size so that we can loop back to the start if we would have had to step past the last legal index in our table. If the try size reaches size -1, then the probe fails. So we keep trying adding on some amount to it, and if we get larger than the size of the array, that means we've tried every index, and so we have to fail in that probing attempt. It does give a deterministic result, and it's required to be able to find the key again later. We have to be able to know where we put it to be able to look it back up. And since we no longer have the nice feature of, well, where we put it is the index it hashes to, we have to be able to redetermine where it would have gone. Long sequences of probing can be costly. It may take some high number of trying to find an empty space, especially as our table gets a higher and higher load factor as it gets fuller and fuller. Here's some of the most common probing methods. Linear probing, so that we do some multiple times the amount that we're told to try. And it's often the case that we can set C equal to 1 so that we just get back the amount. We're just sort of stepping one index to try the next thing. So for example here, we just are sort of adding 1 to it, saying, okay, if this one is full, then I'll add 1 to it and try the next one. And if that's full, I'll try the next one, and so on. So that's the simplest of linear probes, is just to increase by 1. But it's likely to keep the memory cache misses low, meaning you're looking up stuff and not finding it. This will keep it low. Quadratic probing is following a quadratic function with some constant and some linear coefficient possible if you want to change those around a little bit. So we will often set the constant amount to 0 and the coefficient to 1 so that we're just squaring whatever value is given to us. And this will sort of step us through the list a little faster. So we will fail sooner, or we will sort of jump through things faster, not have to iterate all the way through the hash table. But we'll also maybe miss some opportunities with it too. So one can be slower if you're very full to find out that you don't have space for something. And the other one can be faster, but you might miss some opportunities. It is less likely to sort of over-cluster and overfill a small region in the hash table, though. So here's an example of linear probing. If we're working to insert some things and the numbers are already the hash value, we just have to do mod by the size of our array. The size of our array is 7 here. So to insert 76, we mod, we find that its index should be 6. That's fine because it's empty, and we don't have to do any extra looking for it. There is only one probe, meaning the initial attempt there. When we go to insert 93, similarly, it maps to 2. After we do our mod, that's empty. We only need one probe, the initial attempt. We insert 40, it maps to 5. And again, 5 is empty. One probe, initial attempt is all we need. But when we then try to insert 47, it also maps to 5. So we go to look, we can't put it in 5. So if we're doing the linear probing that steps by 1, well, we try 6. No, 6 is full. Then we do the next value, we add 2 to it, which causes us to mod and loop back here up to index 0. And so now we find that 47 can be stored at index 0. Then if we try to insert 10, it maps to 3. That's okay. 3 is still empty, no problem. If we insert 55, which maps to 6, that tries to store at index 6, but 6 is full already. So then it loops back around. It adds 1, which causes our mod to bring us back up to the top. And it finds that index 0 is also full. So then it has to look onward to try index 1. And so it's done 3 probes to find the right location. And you can see, 1, that only one more insertion is required before this hash table is full. So it fills the hash table quicker than the ones that would have buckets. And 2, we are going to have to do a lot of probes once this hash table starts to get full to try to find an empty space for a value. And what's stored at a particular location may not be something that actually hashes to that value. So some of the key properties of linear probing is that we will find an empty slot if our load factor is less than 1. If we're not at 100% full, we're going to find an empty slot. If we assume a uniform hash function, then inserts cause the number of probes to average around 1 plus 1 over 1 minus our load factor. So they're not too bad. We'll do a few probes for finding empty spaces as long as our table is not very, very full. It does suffer from the problem of primary clustering, meaning that we will fill spaces near where stuff was supposed to be inserted. It kind of increases the number of collisions dramatically when you go to insert somewhere in the same area. We saw that with the previous one where we had to try to insert, and then there were things that were filling spots that we had probed to find their location, and we have to keep stepping past all of those ones that are filling up the spots that might have been empty if we had used the bucketing kind of approaches. This can be minimized if our hash function is good, if we're not hashing to an overly clustered region of our space. The performance definitely degrades quickly when our load factor gets greater than 50%. So we can look at an example of quadratic probing where it works well. And we'll look at examples where it works badly as well. So if we go to insert 76, 76 maps to 6, great, 1 probe, no problem. 40 maps to 5, 1 probe, no problem. 48 maps to 6. So we do quadratic probing. We try to put it into 6. We're going to do that tri-value squared. So for 1 squared, that puts us up to index 0 by looping us back around with our mod. We had 1, it would have put us to 7, so that brings us around to 0. Great, 0 is empty, not the end of the world. We try to insert 5. 5 cannot work because the number 5 will also map to 5. 5 cannot work because index 5 is already filled. So our probing tries adding 1 squared, which is 1. That tries index 6. Sorry, that's full. Instead of having to check index 0, we skip a little further past, and we try now 2 squared added to our 5. That gives us 9, which brings our mod around up here to 2. So now we've found that index 2 is empty. We insert 5 there. Okay, great. And if we insert 55, which maps to 6, we would try adding 1. Well, we tried it at index 6, it's full. We try it at index 0, it's full because that 1 loops us back around here. And then we try adding 4 to our index, 10, which a mod of which gives us 3, and we find an empty spot quickly. So the difference here is it didn't overly cluster like the linear probing did. The linear probing, if you tried to insert at 5 or 6, is just going to kind of grow until that region is so full you're never actually finding a space until you've searched through basically the whole hash table. Now, here's a bad example of quadratic probing. We try to insert 76. It maps to 6. That's empty. We're fine. We insert 93. It maps to 2. Still empty. We're fine. We insert 40, and it's empty. We're fine at index 5. And we insert 35. Also empty. No problem. Then we try to insert 47. 47 will map to 5. When we try to do an insertion at index 5, it's full. So we add 1 squared, which gives us 6. We add 2 squared, which gives us index 2 by looping us around. If we add 4, it gives us 9. That maps us to 2. Then we add 3 squared, which is 9, which will bring us back around, I believe, to the 0. And as we keep trying, we find that we're not actually going to find a space quadratically here. The function will just keep popping us onto these locations until our try value gets large enough that we quit and we don't find a location for it. Even though there's empty space, we don't find a location. So sometimes we miss empty spaces with this compared to a linear probing that would step us a little more sequentially through here. Even if our linear factor was not 1, it would still step us a little more sequentially, and we might be able to find the empty spaces there. So sometimes we will entirely miss that there are empty spaces for it when we're using quadratic probing. So key properties of quadratic probing is we will find an empty spot if our load factor is less than 0.5. So not less than 1 like we had for linear probing, but if we're less than 50% full, we can guarantee. If we're above 50% full, we might find a slot, but it's not guaranteed. And generally, if we stay below 50% of our load factor, then it's generally better than linear probing because it doesn't cluster that same way. We don't have to do as many tries. It doesn't suffer from that clustering problem. It does suffer from this problem of secondary clustering versus primary clustering, where we're all very localized. With secondary clustering, the collisions can get into the same probe sequences where you're stepping over the same locations because that quadratic will still follow a function. And so it's going to have similar behavior when you have a collision, and it might fill the slots that that particular collision maps to. The other problem that happens with open addressing is that we cannot just leave a hole when we're trying to delete something, because we then might not find those later colliding keys that we had inserted in there. Because we'll keep looking so long as we see keys that match our hash that we're looking for. And if we stop finding those keys, we'll assume that the thing that we're looking for is not in the hash table. So if something mapped to 5, I'm going to look at index 5, and then I'm going to follow my collision detection until I'm going to follow my probing rule until I find an empty space. And if I found an empty space before I find the value I'm looking for, then I assume that the value was not in the hash table. So if I deleted and I left empty spaces there, I'll find that empty space too soon, and if there was something else that mapped to 5 that I had to put later based on my probing, then I won't find it anymore. There are some solutions to this. We can find the last item in the chain and move it to the deleted key, so we keep following to find the last thing that would have come from my probing on index 5, and I just move that to the space of the thing I'm going to delete. That takes work, though, so that could be a bit of a problem. And we could also use lazy deletion, where we mark the location as deleted for insertion so that I could insert something new in that space if I wanted to. It's usable, but I don't actually remove it so that the next time I go searching, I see that there is data there that matches for key 5 or whatever. There's not an empty space. And I won't treat it as a search result, but I will keep looking according to my probing. And then if I go to insert something later and I end up at that spot, I'll say, oh, that one's marked for deletion, so I can just replace it. Of course, the problem with this is those marked keys still take up space and will contribute to the load factor, and we could actually fill up our hash table with things that were marked as deleted. So for searches in particular, this will slow us down. We will still have to proceed past those marked ones to keep finding values that are later in the hash table. We could fill up our hash table with all of it being deleted stuff except the one value we actually want to find. We might have to search the whole hash table to find that one value. So these are two approaches for collision handling that have their ups and downs. The closed hashing and open hashing, whether we sort of make more space or we use up more of the space that's available and fudge the hash function's index. We will see that there are other aspects of hash tables that can help us to work on performance and help us to handle some of these problems as well.